Welcome everyone. This presentation is devoted to the paper Conditional Mean Risk Sharing of Independent Discrete Losses in Large Pools, co-author with Michel Denuit. The general objective is to understand how individual insurance losses can be allocated within a collective scheme in a way that is simultaneously actuarially fair, incentive compatible, and efficient from a risk-sharing perspective. The framework considered throughout the paper is that of peer-to-peer or collaborative insurance arrangements where participants agree to pool part of their losses instead of fully transferring risk to a traditional insurer. The allocation rule studied is the conditional mean risk-sharing rule, according to which each participant contributes an amount equal to the expected value of their own pooled loss given the total loss observed in the pool. This rule is particularly appealing because it satisfies several fundamental requirements. It achieves full allocation of the aggregate loss, it is actuarially fair in expectation, and it is unanimously preferred by risk-averse agents regardless of the distribution of other participants' losses. However, beyond these normative properties, incentive issues are central. In particular, one must ensure that no participant can benefit from an increase in the total loss of the pool. This leads to the no sabotage requirement, which plays a central role in the paper. The originality of this work lies in the fact that all results are derived in a fully discrete framework, which is the relevant one for actuarial practice, since insurance losses are typically discretized for reporting, accounting, and numerical implementation. A second key objective is to analyze what happens in large pools and to determine whether diversification and even full risk elimination emerge asymptotically. Let us begin with the main contributions of the paper. We study conditional mean risk sharing, abbreviated CMRS, where the contribution of participant I is defined as the conditional expectation of their individual pooled loss, given the total pooled loss of the community. The first key requirement imposed on this allocation rule is the no sabotage condition. Economically, this means that when the aggregate loss increases, no individual contribution should decrease. This property is crucial for incentive compatibility since it guarantees that all participants have aligned interests and benefit from keeping losses small. In finite pools, the paper shows that the no sabotage condition under CMRS is equivalent to Efron's monotonicity property for conditional expectations given sums. This property is classically known to hold under log concavity assumptions. One contribution of the paper is to provide elementary and fully discrete proofs of this result, avoiding arguments based on probability densities that are not applicable here. The second main message concerns large pools. Even when log concavity fails at the individual level, the paper shows that local limit theorems imply that Efron's monotonicity property holds asymptotically on wide central ranges of the aggregate loss. Finally, the paper establishes a strong diversification result. As the pool grows, CMRS contributions converge to pure premia, meaning that individual risk is eliminated and insurance at fair price is recovered in the limit. This slide explains the motivation of the paper from an actuarial and economic perspective. Peer-to-peer insurance schemes aim to reduce conflicts of interest inherent in traditional insurance, where insurers retain part of the premium when claims are low. By pooling losses within a community, P2P insurance promises greater transparency and potentially improved affordability. However, such schemes require allocation rules that are not only fair in expectation, but also robust in terms of incentives. In practice, insurance losses are almost always treated as discrete quantities. This is due to deductibles, policy limits, accounting conventions, and the discretization of continuous severity models for numerical computation. As a result, many classical results derived under smoothness or density assumptions are no longer directly applicable. Moreover, pure conditional mean risk sharing may generate unbounded contributions, which is unrealistic in practice. Real insurance mechanisms therefore rely on a combination of individual retention, pooling of a middle risk layer, and transfer of extreme losses to a traditional insurer. Within this realistic framework, the paper addresses two central questions. First, under what conditions does CMRS satisfy the no sabotage requirement? Second, does CMRS genuinely diversify risk and possibly eliminate it when the size of the pool becomes large? This slide presents the three-layer insurance architecture that underlies the model studied in the paper. Each participant is exposed to a non-negative random loss over a given observation period. After individual retention mechanisms such as deductibles or quota share arrangements, the remaining loss is denoted by Y. Retention plays an important incentive role by ensuring that participants remain exposed to part of their own losses. To prevent unbounded exposure of the pool, a cap M is introduced. Only the truncated loss, defined as the minimum of Y and M, enters the pooling mechanism. Any excess above this cap is transferred to an insurance company through an excess of loss contract and does not enter the pool. This upper layer must be financed individually by the participant. From this point on, the pooled losses are denoted by Xi. They are assumed to be independent and to take integer values between 0 and M. This boundedness assumption is not only realistic from an actuarial standpoint, but also essential for the probabilistic analysis carried out later in the paper, in particular for the use of local limit theorems in large pools. This slide introduces the conditional mean risk sharing rule, which is the core allocation mechanism studied throughout the paper. The total pooled loss is defined as the sum of the individual pooled losses brought by all participants. Under the CMRS rule, the contribution of participant I is defined as the expected value of their own pooled loss conditional on the realized value of the total loss of the pool. This allocation rule satisfies several fundamental properties that make it particularly attractive from a normative point of view. First, it achieves full allocation. When individual contributions are summed across participants, they exactly reproduce the aggregate loss of the pool, so that there is neither deficit nor surplus at the collective level. Second, the rule is actuarially fair, in the sense that the expected contribution of each participant coincides with their expected loss. This property is essential for acceptability and long-term sustainability of the mechanism. Third, CMRS is risk-reducing for all risk-averse participants. Using Jensen's inequality applied to conditional expectations, one can show that every risk-averse agent strictly prefers paying their CMRS contribution rather than bearing their individual loss alone. Importantly, this result holds without imposing any assumptions on the distributions of other participants' losses. The remaining issue, addressed in the following slides, concerns incentives and monotonicity. This slide focuses on the incentive compatibility of the CMRS rule through the no-sabotage condition. Under CMRS, no sabotage means that each participant's expected contribution is a non-decreasing function of the total pooled loss. Economically, this property ensures that the interests of all participants are perfectly aligned. If the total loss increases, no one can benefit individually. As a result, participants have a common interest in keeping losses as small as possible. From a mathematical perspective, this no-sabotage condition is equivalent to a classical property known as Efron's monotonicity of conditional expectations given sums. This property states that the conditional expectation of one component of a sum should be non-decreasing in the value of the sum. In continuous settings, Efron's result is typically proved using arguments based on probability densities. A key contribution of the paper is to revisit this property in a discrete framework. We provide elementary proofs that rely on likelihood ratio ordering and size bias transformations rather than density-based techniques. This makes the no-sabotage analysis fully applicable to discrete insurance losses, which is essential for actuarial practice. This slide introduces the likelihood ratio order, which plays a central role in the analysis of monotonicity. For counting random variables, one variable is said to be smaller than another in the likelihood ratio order if the ratio of their probability mass functions is non-decreasing. Intuitively, this ordering captures the idea that one variable tends to take larger values than another in a strong probabilistic sense. The likelihood ratio order is particularly powerful because it implies several other forms of stochastic dominance and has strong preservation properties under suitable conditions. In the context of this paper, it provides the appropriate mathematical language to compare sums of random variables and their size-biased counterparts. Most importantly, Efron-type monotonicity results can be derived by establishing likelihood ratio comparisons between a random variable and a size-biased version of it, possibly after convolution with other independent risks. This approach allows us to work entirely within a discrete framework, avoiding smoothness assumptions that are unrealistic for insurance data. This slide explains the concept of log concavity and its importance for the no-sabotage property. A discrete random variable is said to be log concave when successive probability ratios decrease. Log concavity implies unimodality and light-tailed behavior, properties that are often associated with well-behaved insurance risks. From an actuarial perspective, log concave distributions tend to exhibit moderate variability and good aggregation properties. A crucial feature of log concavity is its stability with respect to convolution in the likelihood ratio order. Specifically, when a log concave random variable is added to two independent random variables, ordered in the likelihood ratio sense, the order is preserved. This preservation result is fundamental for finite pools because it allows monotonicity properties to be transferred from individual components to aggregated losses. However, the slide also implicitly highlights a limitation. Log concavity is a strong assumption that excludes heavy-tailed behavior. This motivates the asymptotic analysis developed later in the paper, where log concavity is recovered approximately through aggregation in large pools. This slide explains the key idea behind the discrete proof of Efron's monotonicity property, which is central for establishing the no-sabotage condition under CMRS. The objective is to understand why the conditional expectation of an individual loss, given the total loss, is non-decreasing. Rather than working with densities, the proof relies on the concept of size biasing, which is particularly well suited to discrete random variables. Size biasing consists in modifying the distribution of a random variable so that larger values receive more weight in proportion to their magnitude. Intuitively, the size-biased version of a loss represents the contribution of that loss to the total sum. The conditional expectation can then be expressed as a ratio involving the probability that the size-biased loss, combined with the rest of the pool, generates a given aggregate loss. The crucial observation is that the original loss is dominated by its size-biased version in the likelihood ratio order. When the rest of the pool is log concave, convolution preserves this order. As a result, the ratio defining the conditional expectation is non-decreasing in the total loss. This argument provides an elementary and fully discrete proof of Efron's monotonicity. This slide explains why local limit theorems play a fundamental role in the analysis of large pools. In finite pools, log concavity is a strong and often unrealistic assumption, since insurance losses may be discretized, truncated, or mixed with a large probability mass at zero. As a result, the no-sabotage condition may fail for small or moderate pool sizes. When the pool becomes large, however, aggregation fundamentally changes the picture. Sums of many independent bounded losses behave approximately like a normal distribution, not only at the level of cumulative probabilities, but also at the level of the probability mass function itself. Local limit theorems provide uniform approximations that are strong enough to compare probabilities at neighboring points of the aggregate loss. This approximate smoothness implies that sums of losses become nearly log concave over wide central regions. Consequently, Efron's monotonicity property, and hence the no-sabotage condition, holds asymptotically on intervals that grow with the pool size. Local limit theorems therefore provide the key probabilistic tool linking aggregation to incentive compatibility. This slide presents the intuition behind the asymptotic no-sabotage result established in proposition 4.3 of the paper. The idea is to isolate one participant and to decompose the total pooled loss into that individual loss and the sum of all remaining losses. The monotonicity of the conditional expectation can then be translated into a discrete inequality involving joint probabilities of the remaining sum. Using the same size biasing approach as in the finite pool case, the sign of this inequality depends on comparisons between probabilities evaluated at adjacent values of the aggregate loss. Local limit theorem expansions provide precise asymptotic expressions for these probabilities with explicit control of the remainder terms. The analysis shows that for sufficiently large pools, these probability differences have the correct sign on a wide interval centered around the expected aggregate loss. Importantly, the width of this interval grows faster than the classical central limit theorem range. This establishes that CMRS satisfies the no-sabotage condition asymptotically for large pools. This slide explains the risk elimination result established in proposition 4.4. The objective is to show that, in large pools, the CMRS contribution of each participant converges to their unconditional expected loss. In other words, insurance at actuarially fair price is recovered asymptotically through pooling. The proof relies on three key assumptions. First, individual pooled losses are uniformly bounded, which reflects the presence of caps or excess of loss coverage in practice. Second, the variance of the aggregate loss grows at least linearly with the pool size, ensuring sufficient diversification. Third, a mild smoothness condition guarantees that a positive fraction of losses can take consecutive integer values. The argument decomposes the expected deviation between conditional and unconditional contributions into a central region and tail regions. The tail contribution vanishes by the central limit theorem, while local limit theorems ensure stability of probability ratios in the central region. Together, these results imply convergence and hence risk elimination. This slide illustrates how the general theoretical results apply to a concrete and economically meaningful model, namely, binomially distributed losses with heterogeneous probabilities. In this setting, each participant's pooled loss corresponds to the number of claims among a fixed number of trials, with individual claim probabilities that may differ across participants. This framework naturally arises in insurance portfolios where coverage consists of a limited number of homogeneous exposure units such as small claims or standardized benefits. The binomial model satisfies all the assumptions required for the asymptotic results developed earlier. First, losses are uniformly bounded by construction since the number of claims cannot exceed the number of trials. Second, as long as individual probabilities are bounded away from zero and from extreme values, the variance of the aggregate loss grows linearly with the size of the pool. Third, the binomial distribution assigns positive probability to consecutive integer values, ensuring the lattice smoothness condition required by local limit theorems. As a consequence, the CMRS contributions satisfy the no-sabotage condition asymptotically on expanding central ranges of the aggregate loss. Moreover, the conditional contributions converge to the unconditional expected binomial losses. This example shows that the theory applies well beyond simple Bernoulli risks. This slide presents a first numerical illustration based on discretized severity distributions for different risk groups. The figure displays probability mass functions obtained by discretizing a continuous severity model over a finite support. Each curve corresponds to a different risk group, reflecting heterogeneity in claim severity across participants. As risk increases, probability mass progressively shifts toward higher loss values, while the support remains bounded due to the imposed cap. A key point illustrated by this figure is that the resulting discrete distributions are not log concave. This is a crucial observation because it shows that the sufficient conditions guaranteeing no sabotage in finite pools are violated in this example. In particular, one cannot rely on classical log concavity arguments to ensure monotonicity of CMRS contributions when the pool is small. This numerical illustration therefore motivates the asymptotic approach adopted in the paper, even though individual and finite pool distributions may exhibit irregular shapes after discretization. Aggregation in large pools can restore approximate regularity and monotonicity through probabilistic limit results. This slide comments on the second numerical figure, which directly illustrates the behavior of CMRS contributions as functions of the aggregate loss. The left panel corresponds to a small pool, while the right panel corresponds to a much larger pool. In the small pool case, the CMRS contribution of a representative participant is clearly non-monotonic for certain values of the aggregate loss. An increase in total losses leads to a decrease in the individual contribution. This non-monotonic behavior represents a violation of the no-sabotage condition and highlights the incentive issues that may arise in small or moderately sized pools. In contrast, the right panel shows the same contribution function in a large pool. Here, the function becomes monotonic over a wide range of aggregate losses, in line with the asymptotic no-sabotage result established earlier. This comparison provides strong numerical support for the theoretical analysis. It visually confirms that aggregation smooths out irregularities and restores incentive compatibility as the size of the pool increases. This final slide summarizes the main contributions of the paper and outlines directions for future research. The paper shows that, for discrete and bounded insurance losses, conditional mean risk sharing is actuarially fair and always risk reducing. In finite pools, The no sabotage condition is guaranteed under log concavity through Efron's monotonicity, and the paper provides elementary discrete proofs of this result. In large pools, the analysis reveals a more general phenomenon. Under mild assumptions, local limit theorems imply asymptotic no sabotage on wide central ranges of the aggregate loss, even when finite pool conditions fail. Moreover, CMRS contributions converge to unconditional expected losses, leading to full risk elimination and recovery of insurance at fair price. An important direction for future research is to investigate whether these asymptotic properties extend beyond CMRS to broader classes of comonotonic or fair allocation rules, for which incentive compatibility and risk elimination may interact in more subtle ways.